Okay, Remco is going to be our last speaker today. And again, for those of you who do not know about Remco's background, let me mention that Remco did his undergraduate studies at Utrecht University. He also defended his PhD thesis at Utrecht University. Then he went to Canada, to Hamilton, where he stayed for a short while, working, among others, with Gordon Slade. And then he was recruited back to Delft University, where he stayed a number of years. And after that, he moved to Eindhoven and he started a very successful and prolific probability group. And that has been really in the center of attention in probability theory in the Netherlands for many years. And he's also one of the PIs of the big networks program that we're so happy with. And that has been also the basis of a lot of exchange with many groups, including people in India, as I mentioned earlier this morning. So, Remco, the floor is yours.
Thank you very much, and thank you for the kind introduction, Frank. I'll be talking about percolation on random graphs, and I'm particularly pleased to be talking about this because, as you can see from my list of collaborators, there's a high input of very strong Indian probabilists. Amongst them, Sanchayan Sen, who is at IISc in Bangalore. And I'm very happy that you're here, Sanchayan. Also, Shankar Bhamidi, who is at the University of North Carolina. Shovik Dara, who was a PhD student in Eindhoven and is now an assistant professor at Purdue University. And Johan van Leeuwarden, who used to be a professor in Eindhoven, now is in Tilburg. So that's sort of the people who've been with me on this journey. And it's a quite long journey. It's quite a few papers that I'll be talking about, and I will be presenting you 4 theorems on the behavior of, on the critical behavior of percolation on a specific class of random graphs. So as in Luca's talk, here we're talking about stochastic processes on a random graph. So there's double dynamics, always very interesting and fascinating. All right, I'm going to be presenting, okay. It is switched on, I hope. Okay, complex networks and percolation on them. So I was very happy with Pim's talk because he basically explained many of the things that I will be explaining as well, and therefore I can do them a bit more quickly, and therefore I will have a little bit more time to be explaining some of the mathematical ingredients. So here are 2 pretty pictures of complex networks. Complex networks, what are they? Ill-defined. Okay, so they are networks, graphs containing vertices and edges between them, and they're large and complicated. And that actually sort of describes a complex network. You can also think of it as a complex system where the edges somehow indicate interactions between the individuals. It's a large system, and therefore it's complex. So this is a very beautiful picture of an artistic representation of what the internet looked like in 2010. Now, you would think that because all of these networks come from completely different fields, that they will also be totally different. Well, in a certain senses they are, but in a certain sense they are also not. So let me try to explain why actually many of these networks have similarities, and therefore why it's useful to be investigating them mathematically. So first of all, networks are sparse. Pim already mentioned that, and he just stated it as being a property. What I had a bachelor student do is scrape all the data from a website, which is called Connect. And on Connect, there are more than 1,000 data sets of real-world networks reported in the literature. So citation networks, Facebook networks, road networks, all sorts of different networks. And then on the website, you can also find all sorts of characteristics: average path length, clustering, average degree, etc., but also the degree sequences, basically everything. But you can also download all of them. So what I did was, for this whole collection of networks, I looked at the average degree, and I plotted it in a log-log scale, as you often do. And one of the reasons to be plotting it in a log-log scale is that the network sizes vary rather significantly. They basically go from some tens to hundreds, but all the way up to 10 to the power 8 which is humongously big. So if you would put it in a linear scale, all the points would basically be at 0, and then you don't see very much. At a log-log scale, you see that you have all of these different network sizes. And then here you also plot the average degree. And again, that's in a log-log scale, but still, if you sort of squeeze your eyes a little bit, what you see is that this is a cloud, and the cloud is sort of horizontal. Of course, there's variability in the average degree between the different networks. It can be rather substantial, but when this cloud is actually horizontal, then there's no reason to believe that the average degree grows with the network size. Of course, there's variability, but the variability is not due to the network size. It's inherent variability that is in the different origins of the networks, and it is not related to the size. Okay? That is what sparsity means. The average degree is not particularly large. Here, the maximum is sort of, well, a few hundreds. There are a few that are much larger. Sometimes these are multigraphs.
What's the largest network?
You mean which network? Oh, now you're asking a lot. I often get a question about this dot here, which I actually have no idea what it is. I still have to ask my student what happened there. Yeah, it could be Wikipedia. Yeah, oh, there's many Wikipedia networks. Yeah. All right, networks are sparse. But then we've also seen that there's enormous variability in the degree structure, and that's often plotted in this log-log plot. And Pim had a few, I have a few different ones. And a straight line in such a plot indicates a power law. So that means that the proportion of vertices with degree k, which is what I denote here by pk, is sort of a multiple of an inverse power of k. And we've seen lots of these examples already before, also in Frank's talk, where this was the zeta distribution. So somehow the slope here, you should be thinking of being minus tau. Okay? Very good. And of course, you know, when thousands of networks are being investigated, many people investigate these things, and then they report some sort of estimated value for what this power law exponent should be. And what you see is that very often a power law exponent in between 2 and 3 is being reported. Now, you may argue, why is that interesting? Well, tau in between 2 and 3 means that if you have a probability distribution of this kind, tau in between 2 and 3 means that your degree is finite. That's related to sparsity, but the variance is infinite. Okay? And random variables with finite mean and infinite variance tend to fluctuate a lot. So if you have many of them, you see very large values. And this is exactly what you see here, right? You see very large values of the degree. Okay? So tau in between 2 and 3 is special in that sense. All right. So you can again, in the same or in a similar collection of networks, you can now look at the maximum degree, not the average degree, the maximum degree. And what you see is that that actually does seem to be dependent on the network size. And then the average degree seems to be going up as you go to larger networks. Okay? So that is fully consistent with the fact that, you know, if you have a power law, so this is of the order a constant divided by k to the power minus k to the power tau, then you would believe that the maximum value would be proportional to n to the power 1 over tau minus 1. Okay? How should you interpret that? Well, if I were to take n IID random variables from such a distribution, then their maximum value is this. Of course, the degrees in a random graph are not IID, but still, bear with me. They still have a similar behavior. So that would actually mean that if you look at larger and larger networks, the degree should grow like a power of n, and the power that is there should be telling you something about the power law degree exponent. Okay, so we take the log here of d max, that should be proportional to log n. We do linear regression, that's the black line. And you get some sort of a constant, which is irrelevant for me, but you see some multiple of log n. And in a certain sense, this prefactor here should be this 1 over tau minus 1, at least on average, because there's no reason whatsoever to believe that all of these networks have the same tau. Okay? So this is not a mathematical statement, but this seems to be consistent with the value for which 1 over tau minus 1 is 0.519, and that actually corresponds to tau being of the order 2.93, slightly below 3. Okay, so there's reason to believe that you have these networks where you have parallel degree sequences, and larger networks would correspond to much larger degrees. That's what we're seeing here. Yes.
Pairwise correlation between these degrees for these many networks, do they look independent, these degree sequences?
What do you mean? You mean you look along an edge and you see whether they are, that really depends on the network structure. In some settings, there is positive correlation. In some settings, there's negative correlation. Often it depends on the precise network that you have. I think information networks tend to have negative correlations, social networks, positive correlations.
This doesn't affect the maximum degree?
No, of course. I mean, it's related to independence or not, right? But the maximum degree, I believe, grows like a power of n. That's what we're seeing here. Okay. So that was my very first part. We have networks. Now we want to do percolation on them. So what is percolation? Well, percolation you often do on an infinite graph, but still you can do it on any graph. And what you do is you just keep edges independently with a fixed probability p. You can think of this as, roads are independently being closed, and what you're interested in is, can you still travel from A to B? With the roadblocks that are there. Okay, and what on infinite graphs exists is that there is a phase transition. It's one of the simplest statistical physics models where you see a clear phase transition in the infinite system. And what this means is that there exists a certain PC, which is often in between 0 and 1. And for p smaller than that PC, there's no infinite connected component. You have an infinite graph, but by breaking all these edges randomly, all the connected components become finite. Whereas if you take P to be strictly larger than PC, you will have an infinite connected component, sometimes one, sometimes many. That depends a bit on the structure of the graph. Okay, so this is a very simple example of a system with a phase transition. And as I said, most infinite graphs have a PC that is strictly in between 0 and 1. An exception is the one-dimensional line where PC is 1. There is also some cases where PC is 0, but think about PC being in between 0 and 1 strictly, and then you have a non-trivial phase transition. And then you can try to investigate what the structure of the connected components will be. And then the most interesting things are happening very close to this PC, because there might be a very thin infinite component, or there might not be an infinite component, but you may have very big components. So you can think about what the structure is of these very large components, very close to the critical value. And these turn out to be self-similar or fractal or whatever. And that's very, very cool. This is a topic that has attracted a lot of attention. For example, for two-dimensional analysis, for which there were 3 Fields medals given to, amongst others, statistical mechanics in 2 dimensions. And percolation played an important role there. Stas Smirnov proved that the 2-dimensional percolation on the triangular lattice is conformally invariant, and identified all sorts of critical exponents related to that that were already believed to exist in the physics community, and that were then, for the first time, fully, rigorously proved. Now here we're not going to be thinking about lattices. We'll be thinking about random graphs. In particular, random graphs are finite. And of course, phase transitions are wonderful, and we're talking about infinite components. Well, if you start out with a finite graph, you can't have any infinite components. So how can you even interpret what a phase transition is? It's difficult. And in fact, I don't have a clear answer. There's a few papers here that I've listed that defining what a critical value is for a finite system tends to be difficult. Okay? We often, in special cases, have very clear ways how to do it, but they're a bit ad hoc. They sort of depend on the precise setting that you're interested in, and there you can define them, but for a general setting, it's a bit harder. But what you see in many of the examples is that there exists some increasing one-parameter family of critical values. Okay, so now anything you're going to be looking at a finite system is going to be continuous. right? It's going to be a finite degree polynomial in P, whatever you're looking at, any expectation or probability or whatever. So you can't expect any discontinuities to happen. So therefore, you can't, phase transition should be interpreted in the right way. The interpretation is that there's some sort of critical window. It's this function, which is a one-parameter family of values. And if you stick in for this lambda here something that tends to minus infinity, all components become very small. And if you let this lambda n here tend to infinity, you're going to have a unique largest component of close to deterministic size. So this is what you should think of as being the equivalent of the giant component. Okay? But if you take lambda to be fixed, then something interesting happens, and what you're going to be seeing is fractal random components of some sort of a mesoscopic size. So something in between finite and order n. Order n is macroscopic. You really have something that contains a positive proportion of the vertices. That's not going to happen because you're close to criticality, but also these large components are going to be quite big. Some power of n, fractal-like. And what we're going to be doing is looking at percolation on highly heterogeneous random graphs. The fact that we're looking at these highly heterogeneous things is related to these power laws. We have a high amount of variability in the degree structure, and the question is, how does that permeate into the behavior of critical percolation? That's what we're going to be looking at. So let's first look at network models and their giants. If you want to somehow locate where the phase transition occurs, you gotta know somehow in which regime you're going to have sufficient connectivity, meaning that a positive proportion of the pairs of vertices is going to be connected to each other, and where you don't. Okay? That's what is sometimes also called the phase transition for random graphs. And I'll be doing this for one specific random graph model. And this is called the Poissonian random graph. And I'll explain a bit later why this model is actually very special. I'm going to be making some notes so that you don't forget what this model is. And in fact, there's two settings here. There's a single edge setting, and there's a multi-edge. And they're very closely related. So these are examples of what are sometimes called inhomogeneous random graphs, rank 1 models, or they come by with very many different names. And here, the probability that an edge ij is present, I'll often denote by this by pij, is going to be 1 minus e to the power minus wi, wj, properly renormalized, where this normalization is the sum of the weights. So every vertex has a weight, and depending on the weight, you're more or less likely to see an edge between two vertices. Okay? Vertex I has weight wi, vertex j has weight wj. What you see is if these weights are very big, you're very likely to see an edge. If these weights are very small, you're unlikely to see an edge. Okay, so vertices with high weights are going to have many edges. Vertices with high weights, therefore, are going to have a very high degree. Now, the multi-edge case is very similar. You can think of this as being the probability that a certain Poisson random variable takes on a value at least 1. So here, we're going to have multiple edges. So the number of edges between I and j will have a Poisson distribution with parameter wi times wj divided by ln. So if you wish, and all of these things are going to be independent over the different edges. If you wish, you can think of this setting as being a collapsing of this setting. So if you have multiple edges here you collapse all of them to 1. Then it's exactly the same model. So you can think of the two models as living on the same probability space and being coupled to each other if you wish. And then clearly this one will be bigger. It's going to have more edges. Now, of course, if you're thinking in terms of connectivity, the multi-edges don't do anything. So the graph distances in these two graphs will be exactly the same. But bear in mind, we're going to be doing percolation. So if I have 5 edges and I percolate them independently, I'm much more likely to retain one of them than if I first collapse them and then do percolation. There may be a big difference, or there may not be. Okay? But that's the crucial point here. I'm sorry?
The second system is easier to analyze. Is that why we're looking at it?
You will see why we're looking at it. Bear with me. I should have answered that question at the end of my talk. So that's my random graph. Now, what I also want is that the degrees obey a power law. And the motivation in this model is that you can somehow moderate the degree inhomogeneity by choosing your weights cleverly. Okay, if you choose all of them the same, you have an Erdős-Rényi random graph. There's not a lot of variability in the degrees. But if you let these WIs vary a lot, the WI can be interpreted as being the expected degree of vertex I. So if WI happens to be extremely big, you're likely to have a very big degree of that vertex. Still going to be a random variable, but you know, if WI is very big, you also expect the degree to be very big. Okay? So you can make the graph very inhomogeneous by making the weights very inhomogeneous. That's the point. Okay? And if you want to have a power law, then you should start with a distribution function that obeys a power law of this kind. So this is a distribution function. This is the tail distribution, the probability that you're larger than k. That decays like an inverse power of k. And then what I do is I take 1 minus this distribution function inverse in j over n. And it turns out that the weight structure is then of this kind. Okay? So in the rest of my talk, you can just assume that Wj is this Cn divided by j raised to the power 1 over tau minus 1. And bear in mind, this 1 over tau minus 1 is exactly the same as the one that we see here. Because vertices of this weight, so vertex 1, for example, has the highest weight, it's going to have a weight that is of the order a constant times n to the power 1 over tau minus 1. It will also, with very high probability, have a weight that is of that order. So this n to the power 1 over tau minus 1 really is the maximum weight and also the maximum degree. Okay. Very good. So that's my model. So when do models of this kind have a giant component? Well, that's well known. This is a special case of what is sometimes called an inhomogeneous random graph. There's a beautiful paper by Bollebach, Janssen, and Reardon from 2007. It's 120 pages. It's almost a book. And they investigate all sorts of different settings, special cases, etc., and many results in full generality in settings where somehow the edge probabilities tend to be of the order 1 over n. And that's also the case here. If this ln, the total weight is of the order n, then most of these edge probabilities are going to be of the order 1 over n. And they've identified where the critical value lies, what graph distances are, what the diameter is, all sorts of things. And this is one of these results. It turns out that if you have to take a value nu, so this f is the distribution function of these w's, and then nu is a certain parameter, you want that to be larger than 1, then there is a giant, and then you can perform percolation. And if you do percolation, then you can have a largest component that has linear size if your p is larger than 1 over this value. And it will have a largest component that is smaller than linear, so basically dust, when p is less than or equal to this value. So now at least we know what the first order magnitude is of where the phase transition occurs. Above this value, you're going to have a giant component that has linear size, and below it, it has smaller size. How small, we don't know, but it has smaller size. Okay? So in this sense, I would argue that the critical value in my system is 1 over this number.
Here is like that lambda parameter.
I'm sorry?
U here is like that lambda parameter.
The lambda parameter?
That one
No,
parameter.
no, we'll get there. We'll get there. It's not. Because then you're already at criticality. We're not yet at criticality. And this 1 over nu here, you can think of this nu as being the expected 4 degree of a vertex. Okay? So suppose you start from a vertex and you want to identify whether it's in the giant. well, then from that vertex on, by exploring, you should be able to go pretty far. Okay? I start exploring from that vertex, I look at a neighbor, and then I start thinking about what more neighbors does this vertex have? That's the forward degree distribution. The expectation of that is exactly this value. That's a computation you can do. Okay? That's related to the local limit being some unimodular branching process. And again, what you see here is some sort of size biasing. We've already seen this in the configuration model as well. Okay, so that's where the second moment comes from. Okay, so if your expected forward neighbors in a uniform edge is larger than 1, then you sort of believe that you can go further. Whereas if it's smaller than 1, you somehow you locally decrease, and therefore you should die out. That's the philosophy behind this. Of course, proving this is a different story, but that's what it is. Now, in particular, if this second moment is infinite, which occurs when you have infinite variance degrees, then you look at this value, 1 over this value will be infinity, 1 over this value will be 0. What does that mean? Well, it basically means that if I perform percolation on this graph, for any strictly positive value, I will always have a giant. The giant will, of course, become smaller as p becomes smaller, but for any positive value, I will have a giant. Whereas if you have a critical value that's strictly positive, then you're going to see a giant up to some point, and that point is strictly positive, and then below that point, all of a sudden, the giant is gone. Robustness of the giant is actually pretty weird, right? It basically says, it doesn't really matter, even if I just keep 1/1,000,000th of my number of edges, if I let my graph become infinitely big, in the end, I will still have a positive proportion of vertices that are connected to each other. Of course, the proportionality constant is going to be very tiny, but still, it's a weird notion. That's called robustness. All right. So in a certain sense, this identifies where the phase transition lies. It doesn't describe yet what the nature of the connected components is around this critical value. How large are the components there? Well, they're probably going to be relatively big, but they're smaller than n. So how large are they really? Okay, that's the question that we're going to be investigating in what follows. So that's critical percolation on Poisson random graphs. It turns out that there's various settings. I will have 4 theorems and 4 different settings where the scaling behavior is different. And the scaling behavior differs in, or the source of the difference in the scaling behavior really comes from the level of inhomogeneity that is present in my weight structure and therefore in my random graph. Okay? So if it's sort of a roughly homogeneous setting, you're going to be seeing one sort of behavior. If the weights are somehow varying quite a bit, but not with infinite mean, there's going to be a setting. If the weights are varying a lot with infinite mean, there's 2 settings, and it's there where the multiple edges and the single edges are going to make a difference. We will see. Okay, so that's the 4 different settings. So here I'm looking at the very first setting, and in this first setting, I have inhomogeneity, but the inhomogeneity is weak, and it's so weak that I can assume that the third moment of the degrees is finite. So in this setting, this third moment is finite precisely when tau is larger than 4. Okay? So we have relatively thin degrees, but if tau is larger than 4, this could still be roughly n to the power of 1/3. That still can be quite sizable, right? But somehow the inhomogeneity washes out in this sense. All right, so how does this go? Well, there's a construction using Brownian motion minus a parabola. This is a stochastic process that is actually quite nice. So you start with a regular Brownian motion with a certain standard deviation, which is given in terms of this. Then you have some sort of a linear drift, which depends on some value lambda. Oh, here I didn't write down what the p is. I will do that on the board. And then there is a quadratic polynomial or a quadratic drift. So let me make a picture of this process. It's called a Brownian motion minus a parabola. So I'll do this for lambda positive. So if lambda is positive, you're going to be increasing linearly first. That's the lambda times s, which comes with a plus sign. But there is a negative term here as well, the minus s squared times whatever. So eventually you're going to go down. Okay? So that's the mean of this process. But then, of course, you have the Brownian motion that is going to be fluctuating around it. Okay? I'm not very good at drawing Brownian motions, but I'll try my best. So you get something like this. Of course, it's a continuous process, but it's, of course, much more irregular than this. Okay. And actually, this continues forever. And what we now have to do is we have to look at the excursions of this process. What does that mean? So you start here, there's a little stuff happening here, it doesn't matter. Here there's a new minimum being reached. This is an excursion. Okay? After that, the process goes up for quite a long time. Takes quite a while before you see the next excursion. That occurs here. That's the next time we run into our minimum. So this is an excursion. And in fact, in this case, it's very likely to be the largest excursion. There are many more excursions here. Right? So you may have a few here, then you may have one here, you will have one here, and you will have one here, etc. Okay, so these are all the times in which you reach your next minimum. Okay. That you can define this is already highly non-trivial, but you can. But what is even more interesting is that you, in this setting, can order the excursions according to their size. That really has to do with this quadratic drift going down. At a certain moment, it drops down so quickly that it becomes very difficult to not just race down very fast, and therefore your excursions are going to become tiny. Okay? So certainly when lambda is positive, you're going to be following this parabola for a time, and then here you're going to have rather a sizable excursion. It will be pretty difficult to have one that is as large as this, because you would have to go up for a very long time, and then go down again somewhere. But then you're very far away from your mean. That's just not going to happen. Okay? What I didn't say here yet, oh, I did say that. What the percolation parameter is. So remember, 1 over nu was PC. So here we're taking PC, and we're multiplying it by 1 plus lambda, that's your location inside your critical window, divided by n to the power 1/3. So 1 plus this thing that is very small is going to basically be 1, but this tuning allows you to sort of see a little difference, for example, here in the drift. Okay, because the lambda really is the derivative of this mean at 0. So if lambda is like this, you immediately go down very quickly. If lambda is like this, you're going to go up for a very long time and only later go down, right? So the lambda plays a crucial role in the distribution of these excursions. All right. And then, as it turns out, if you look at the ordered cluster sizes, that's this. So I look at the connected components in my percolated graph at this very particular value of P, which I claim to be the critical window. You order these excursions, and you look at those as an infinite sequence. Of course, on any finite graph, it's a finite sequence, so you just put a lot of zeros behind it. But eventually, you're going to get more and more of these clusters. As an infinite sequence, this converges in distribution to these ordered excursions. Okay, that's a beautiful theorem by Aldous, who proved this first for the Erdős-Rényi random graph, where the edge probabilities are basically 1 over n, plus times 1 plus lambda over n to the power 1/3. But it turns out that this is true generally. Okay, so you can see this as a form of universality. Where if your random variables are sufficiently concentrated, they're sufficiently nice, again, the same Brownian motion limit appears, apart from a certain rescaling of your coefficients. So here you see this lambda appearing, this sigma appearing, here you see the sigma squared appearing, here you see mu appearing, which is the expected value. So the parameters of your weight distribution appear in your formula, but only as scaling factors, just like in the central limit theorem. Okay?
Is there a link between the fact that you have the 1/3 and that sigma squared has a third moment of W's, or are those completely unrelated?
That's a good question. I think they're unrelated, but you can really think of this as being a variance of a process, and it's the variance of the exploration process. So you start exploring from a vertex, you start exploring further vertices, and it turns out that the variance of, let's say, the number of forward neighbors is asymptotically this.
Yeah. But is that then related to the -3, or is there another intuition why it should be a third?
Well, the intuition is the same as for the Arijit graph, and that comes from a depletion of points effect.
Okay.
So once you start exploring, you're exploring clusters of size n to the power 2/3, and that somehow shifts you in the critical window. That's where the 1/3 comes from. But it's a, yeah.
How universal is this with respect to the connection probabilities?
I would guess quite universal, but you have to be a little careful. Because your exploration process should basically be converging to a Brownian motion, leading order. Right? So in the next theorem, we'll see an example where this is not true. All right, so what we see here is that the largest connected components have size n to the power 2/3 in distribution. And in fact, all of these random variables are strictly positive, almost surely. So really these clusters, you have infinitely many clusters in the large graph limit of size n to the power 2/3, but their prefactors will become smaller and smaller when you're looking at more and more of them. Okay? And n to the power 2/3 really is mesoscopic. It's not n, but it still grows relatively quickly. Ooh, that's an appropriate power of n. Now what happens when you have infinite third moments? So that corresponds to tau in between 3 and 4. You have a finite second moment, because you're larger than 3, but you have an infinite third moment. Then it turns out that the maximum degree here, which is related to this value, is of size much larger than n to the power 1/3. That actually means that if you start exploring and you run into one of these hubs, you actually are pushed up rather significantly. So again, you can do a scaling limit of the exploration process, but this process is going to have jumps corresponding to finding hubs. Okay? So the process is different. And that also means, by the way, that the scaling is different. So rather than it being n to the power 2/3, it's now n to the power tau minus 2 over tau minus 1. And that's a little bit smaller than 2/3. That also always surprised me. I would have expected that more heterogeneity would give you larger critical clusters, but it gives you smaller critical clusters. Bit weird. Okay? And also the location of the critical window is a bit different. It's no longer n to the power minus 1/3, but it's n to the power minus tau minus 3 over tau minus 1. Bear in mind, all of these exponents are such that if you stick in 4, which is sort of on the boundary, you get exactly the ones from the previous case, the lightly homogeneous case. So somehow it connects up smoothly, but the structure here really is different in the sense that if you take two vertices, two of the vertices with the highest degree, let's say vertex 1 and vertex 2, they have the highest degrees. They will be with positive probability connected to one another, even after percolation, but they will also be with positive probability not connected to one another. Okay? So really it's the hubs that are running the show, and sometimes they're in the same component, and sometimes they're not. Okay? All right. So how does one prove this? This is a very brief slide because I want to continue with the second part where we really have a very strong inhomogeneity. I already mentioned that sort of these processes come from exploring clusters. So, for example, you take a uniform vertex, you look at its component. Very likely it's going to be very small. If it's very small, you take another vertex uniformly at random that you haven't seen yet, you start exploring it. And you continue this indefinitely until you're done. At a certain moment in time, by rare fluctuations, you might see a cluster that is actually fairly big. And that's the one that you're going to be keeping. And if you track how many vertices you should still explore, you get something like this. That's precisely what this is. Okay? So you're basically doing this, this exploration. Now, you would maybe be led to believe that this exploration would give you Brownian motions or random walks or whatever, but there's delicate things happening. When you are exploring, and you've explored quite a bit, you have fewer vertices. So in a certain sense, your graph has become smaller, and therefore there's less sort of opportunities for you to create a very big component. That's very closely related to what you see here. If you're quite far along in this exploration process, if you have a negative drift, that comes from this depletion of points effect. You have explored part of the graph. Of course, all the connections between the parts that you haven't seen are still totally independent, but there's just fewer of them. And in this setting, it's not only that there are fewer of them, also their weights have gone down, because you're more likely to be exploring the high weight vertices first. So you have a double effect. First of all, a depletion of points effect. There's fewer unexplored territory. And then secondly, also the vertices that are left tend to have smaller weights. Okay? That's why this process eventually starts drifting down. And there's a different case. So when this third moment is finite, your steps of the exploration process have finite variance. And when you start summing things that have finite variance, you think that there should be something Brownian. Well, that's exactly the Brownian picture that I'm showing here. Okay? And I call that power to the masses. In a certain sense, you know, even when you have very high weight, you're not more likely to be in a large component. The vertex with the largest weight could be in the largest component or it could not be, but the probability that it is actually quite small. Okay? So it's basically the fact that you have very many vertices that allow you to have these rare, very large clusters. But there's nothing special about the weight structure of the vertices in them. That's quite different in the infinite third moment case. There really the height weight vertices dominate the exploration, and you're sure that there's a few hubs in the largest connected component. Right? And also the hubs are with positive probability connected to one another. Here, the hubs are with probability vanishing connected to one another. So it's really a different structure. Here, the hubs play a dominant role in the exploration. Here, they don't. Okay? Inhomogeneity matters. Inhomogeneity doesn't matter.
Can you count the number of hubs?
Well, I mean, you basically have them on all scales, but in a certain sense, there's a finite number of them. But if you're interested in the number of vertices that have a weight larger than epsilon times n to the power tau minus 1, it's going to be finite, but it will explode when epsilon tends to 0. And it's really the large ones that matter the most. But you can't ignore any of them. So all the hubs matter. All right. What happens when you have infinite variance degrees? So now you have huge amounts of inhomogeneity. And the inhomogeneity is so strong that however small you pick your percolation value, you will always have a giant. Okay, how can you even talk about critical percolation? Well, what you could do is take an appropriately chosen sequence of values that vanishes. But then, of course, you need to know what it means to be critical. Okay? I still haven't answered that. I've just given you examples where you see critical behavior and told you these are the critical windows. Okay, here it's tricky. How should you choose them? So the difficulty in the scale-free regime is that the degree distribution has infinite variance. So the largest degrees are much larger than square root of n. They're of this order of magnitude. And if tau is in between 2 and 3, this exponent is in between 1 and 1/2. So it can go all the way up to 1. When it's 1, the degree of the vertex is almost sort of macroscopic. Right? But it's always strictly smaller than 1. So you never go to 1, but it can be arbitrarily close to 1 in the exponent. Okay, so these hubs really are gigantic. And in our setting, if you take 2 of these hubs, that's why square root of n is so important, this will be order n. If this is much larger than square root of n, and that is also much larger than square root of n, this number here is going to be very large. Now, Poisson with a very large parameter is going to be very large. So you're going to have tons of edges between these hubs. That's what makes this very special. So if tau is larger than 3, then these numbers are always still going to be small. So even between the hubs, it's unlikely to have an edge. Okay? They're not directly connected to one another. All right. So the question is, what is the appropriate critical value, and how does it depend on the network structure, and what is going to happen? Two theorems. Now we see the difference between the multi-edge case and the single-edge case. The multi-edge case is easier, because if you apply percolation to Poisson, you're still Poisson. Okay, so there is an exact renormalization that you can make use of, which is actually very convenient. I'm claiming that the critical value should be taken in this form. And on the next slide, I will explain why you have to take exactly this form. But if you take this form, for an appropriate value of lambda, take it to be strictly positive, because otherwise it makes no sense. For any value of this lambda, you're going to see convergence of the largest connected component, properly rescaled with this n to the power tau minus 2 over tau minus 1. In fact, the same tau minus 2, tau minus 1 as we see here. But of course, tau is a different value. After this rescaling, you again see a limit where all of these random variables are strictly positive. Okay, so it looks a lot like the previous case. The only difference is that now my p's are vanishing with n. You really have to take them down to 0 before you start seeing anything critical. And critical here, I really mean that these are appropriate random variables. Okay, they're not deterministic. And they're all strictly positive. Now, the power of Pn was predicted in a few physics papers. And one thing that you can also think about is that this power of n, which I've written here this way, you can also think of it as being this. And what is the interpretation here? Bear in mind, n to the power 1 over tau minus 1 is the degree of the hubs. Each of the edges that comes out of the hubs will be kept with probability Pn. So this is the expected degree of a hub. And that's exactly the size of your components. However, a component may consist of several hubs. The hubs have an intricate interconnectivity structure. Okay? But it's basically the hubs and their connections together with their neighbors, and that's everything. Okay? So the hubs are really very central in this whole business. And this value here, this exponent, is in between 0 and 0.5. So clusters, critical clusters, are relatively small. So how can one understand this? So as I said, the largest degree, the vertices, have a weight that is of this order of magnitude. And therefore, the number of edges between two hubs, it's actually highly concentrated because this value is going to be very large, is of this order, n to the power 3 minus tau over tau minus 1. And that's precisely, it's growing with n, it's a positive power of n, and it's exactly, this is exactly 1 over that value. So that actually means I have a Poisson variable with a very large parameter, and I'm keeping them all with probability basically 1 over that parameter. That means that I'm going to be keeping a Poisson number. Okay? So that means that I'm going to be keeping a Poisson number of edges between all the pairs of hubs. Where how many I keep is sort of dependent on, well, how hubbish are you? What is your I, right? What are the I and the J? They are playing a role as well. So the surviving edges are random. The surviving edges between the hubs are random for this choice of Pn lambda. So you can basically look at the interconnectivity structure between the hubs, the direct connections between the hubs, and then add their neighbors. That's going to give you your clusters. That's it. And we have extra proofs that actually show that this really is the critical window. So things are different if you're much smaller than this, this choice of P. And things are also different when you're a bit larger than this. So if you take here a lambda n that tends to infinity, then you see that there is one giant component that has basically deterministic size. If you're much smaller than this, then basically all the hubs are isolated, and the largest hub together with its neighbors is basically going to be the largest component. Both of these are deterministic and not very interesting. It's only in this critical window that you see this intricate connectivity structure between the hubs and random connectivity structure between the hubs appearing. And you have this fractal scaling. All right, last theorem, single edge case. Well, first of all, you have to pick your P in a different way. Lambda divided by n to the power 3 minus tau over 2, which turns out to be much larger. That it's much larger is not so strange, right? Because we were seeing that these multiple edges between the hubs were so important. Now we're collapsing all of them before doing percolation. So the hubs are not going to be connected to each other whenever you take a P that tends to 0. Okay, so the structure has to become significantly different. And it's so significantly different that you have to take a larger value of P in order for the thing to become critical. Okay, that's one. The second thing is that in my previous theorem, actually the scaling, I mean, the limit in its distribution depends on lambda, but the qualitative difference is not there. For any lambda, it's basically the same, right? These lambdas or these gammas always have a strictly positive support. And of course, they become smaller when lambda increases. And so there's some monotonicity in the lambda, but qualitatively, they're always the same. They're always strictly positive. Oh, here, that's not the case. So depending on lambda, you can have different behaviors. So if you take lambda to be sufficiently small, smaller than some sort of lambda c that we explicitly compute, it's a number, you see that your clusters behave sort of fractally. There's some power of n, a very weird power of n. So it's a quadratic in tau divided by a linear in tau. You can't really make it nicer than that. That's just what it is. And the convergence is, again, to a sequence of random variables that is strictly positive, very alike in my previous statement. But if you take your lambda to be larger than the critical value, all of a sudden your cluster becomes, to leading order, deterministic in size. Okay? And not just is it deterministic, but actually, if you divide it through by square root of n, it converges to a limiting number. That's very weird. We call this a tiny giant. Because it's exactly, I mean, in terms of its behavior, it's exactly the same thing as what is happening for other random graphs around the critical point, right? If you take a small value, you basically see dust. If you take a large value, you have a giant. But the giant then generally has a linear number of vertices in it. Here it only has a square root of numbers in it. Square root of the size. And not only that, but if you look at this exponent, which is very weird, if you make a plot of it, it looks like this. I think I have just enough here. So tau ranges between 2 and 3. Here you have 1/2. That corresponds to this exponent. The other exponent does something like this. It's 1/2 here, it's 1/2 there, and the lowest value is something like 0.44. That's almost a half, right? The difference is 0.06. So if you want to see that in a simulation, you have to take an order of magnitude for which sort of n to the power 0.06 becomes sizable. No way that you're going to be able to do this. So this was not known by physicists, and very clearly so. So with Dima-Kryukov, we've been trying to see this in simulations, and we've still failed. Yes? Yes. I didn't write that, but it is. Yes. Good question. Yes. Yes, we do, as some sort of nasty integral. I don't think we can compute it. We can compute lambda c, though, explicitly. Any other questions?
Tiny giant stays different, the rest of the graph stays.
I'm sorry?
Tiny giant.
Yeah, that's a good question. So the second largest component is smaller, but we don't know how large. That's an excellent question. I would love to answer that, but it's hard. Yeah.
Do you expect the second critical window around?
Excellent question as well. I expect the phase transition to be infinite order. And we don't really know how phase transitions around infinite order phase transitions occur. So there's more, let's say, random graph models where the phase transition is believed to be infinite order, preferential attachment models and uniformly grown random graphs. We don't know what the critical window looks like or how to do that. It's really weird. So I don't have an answer. I believe here it to be the same. I have good reasons for that, but we have not proved that.
Do you have a sort of heuristic argument for why you think?
Yes, we'll get there. Any further questions? So, a bit of history. So with Shovik, we were thinking a lot about this, and we figured out that this was the right value. And then we started doing computations. We were able to show that for lambda sufficiently small, everything was nice, and we saw this behavior. And sort of thinking back about the previous theorem, we were thinking, okay, that should actually be true for every lambda. So we worked very hard and very long in order to prove that. We didn't succeed. We didn't get anywhere. And then Shankar visited us. I think this was actually for the PhD defense of Shovik. And sort of we explained to him and said, yeah, well, maybe it's not true. Wait a second. What's happening here? Well, he turned out to be right. And he had a very good pointer for us, which I'll get to on the next slide, or on the slide after that, actually, for why there would be different behavior. So let's get into that. So as I said before, you have hubs. They have a high weight, n to the some power, which I call here alpha. Now, of course, the direct edges are not going to play any role. They did in the multi-edge case, but they don't now. So if you want to connect two hubs, how are you going to do that? Well, not through a single edge. The easiest second way, it would be by a two-hop path. So you start from your hub, you go to another vertex, don't care which vertex, and you go back to your second hub. In fact, all of these two-hop paths will be independent. Very nice. Okay? So you can do some arithmetic. Well, what is the expected number of two-hop paths between two hubs? Well, it's this. This is the probability that there is an edge between I and V. V is the intermediate point. This is the probability that you have an edge between V and J. J is your other hub. You can compute this, and this will be very close. I wrote equality, that's not exactly true, but it will be very closely related to the rescaled version of the weights. So that's going to be a number. The rescaled version of this weight, the other hub, times some factor of n. Bear in mind, this factor of n is closely related to the percolation threshold, because if I want to retain the two-hop path, I'm going to be retaining each of the edges independently with probability Pn. So the number of surviving two paths, surviving percolation, is Pn squared times this. But remember what Pn was. It has this n to the power minus 3 minus tau over 2. If I square that, I get, and divide through, I get n to the power 3 minus tau. So that means that if I multiply this thing by Pn squared, I get something that converges. And as I said, all of these things are independent. So what you can expect is that a Poisson number of them survives. But of course, the Poisson number is going to be depending on, well, how large I is and how large J is. So you're going to have inverse powers of I and J. So for large I and J's, these probabilities will be small, but for small I and J's, these probabilities will be large. Okay? Okay. Very good. As it turns out, this is a bit of calculus, it's just a sum, right? So not so worried about that sum. If you look at this Pn lambda squared and multiply this expected number of two paths between I and J, that converges to something. Some function of I and J. That function of I and J takes this funny value. You take the minimum of I and J to the power alpha, the alpha which was 1 over tau minus 1, and then the maximum of I and J to the power minus 1 minus alpha. If you were to take an inhomogeneous random graph with this as a kernel, it's bound to have an infinite order phase transition. That's why I believe it has an infinite order phase transition. Now this H here is homogeneous with degree minus 1. Okay, so if I stick in T times I and T times J, I'm just going to get a factor of 1 over T out, and I still get the same H. The exponents here sum up to minus 1, basically what happens. Okay, and such processes on, let's say, Z plus, on the positive integers, so the positive integers correspond to all my hubs, but I have infinitely many. It's related to your question about how many hubs do you have. You really need all of them. Such percolation processes have been investigated by de Ret and Kesten in the 1990s paper that was almost forgotten. Beautiful paper. And it turns out that this graph has a phase transition. And the phase transition is weird, and certainly people who are doing percolation theory will think, how can you have a phase transition in a one-dimensional percolation process? Well, you can. And this has a phase transition at lambda c. And the phase transition at lambda c is that below lambda c, the limiting graph will be disconnected. Above lambda c, it will be totally connected. So the whole of ZD will be connected. Bear in mind, what does this correspond to? Above lambda c, in my percolated graph, all the hubs will be connected. They're all into one big component. That's going to be my tiny giant. And for the rest of the graph, there are no hubs left anymore. So their connected component should be really small. So there's a unique giant. And it has a deterministic size. Okay? Below this lambda c, well, my hubs are somehow, they have intricate connectivity that is random. Well, you know, their sizes are going to be whatever, I don't know. But you know, the connectivity is random. That corresponds to the subcritical regime. Okay. I'm out of time. I had wanted to say more, how we prove this. Don't have time for that, but okay. Conclusion about percolation in general. Scaling limits of cluster sizes in Poisson random graphs depend sensitively on the number of finite moments of the degrees. In particular, finite third moment, finite second moment. Okay? So that gives three regimes that behave sort of rather differently. Scaling limits within the critical window after you've identified it appropriately are described by excursions of limiting exploration processes. So you explore clusters one by one, you take a scaling limit of that, and in terms of, let's say, the excursions of those, you can describe what the cluster sizes are. And these processes behave rather differently in the finite versus the infinite third moment setting. There's lots of extensions to metric conversions and so on. That's also where Sanchayan was involved. And in the scale-free setting, this was very surprising to us that the... I'm 5 minutes over?
At 4:20.
Yeah. Yeah, sort of. Yeah.
I should stop. This is my last slide.
Yeah, right.
But I had 1 hour, right? So then I'm 1 minute over.
50 minutes with that.
Okay, never mind. Okay. Single edge constraint, you have a finite critical value. That was the weirdest thing. And you have a tiny giant that is roughly deterministic. And there's a lot of literature that you can see if you download the slides. Thank you.
Remco. Questions? You want to ask the first question, Siva?
So this, are there any other models where this 1 over root 10 is available for the first component or any other scale
The root 10, yeah. So we started working on the configuration model. And we believe that something similar should be true for the configuration model, where in the scale-free setting, you should look at the erased model, which does exactly the same thing as what you do here. Namely, if you have multiple edges, you collapse them and only then do percolation. It's exactly what we do here. That model is a bit more difficult. So the results for the multi-edge we have extended, but the results for the single edge we haven't. Turns out to be more difficult. The independence of the edges really helps. So we don't have the square root of n result, but we do have the theorem 3 result for a configuration model. But I do believe it to be true. And in fact, somehow the edge probabilities are very alike. So yeah.
This is a standard question.
I guess this is a standard question. What happens in the tau 3 and tau 4?
Critical, you mean the crossover. Logarithms here.
Yeah, 2 answers. So let's look, for example, at this one. So there you can have tau equal to 4 and still, by your slowly varying functions, have a finite third moment weight. Then this result still applies. But if you don't, then I'm expecting sort of slowly varying perturbations. In some settings we know this, in some settings we don't. But it's a lot of work generally. And then the question is it really worth it? I don't know. I think it's interesting. But... I'm sorry?
Can you speak up? Sorry?
The order of the diameter in the in each of the two cases? That's a good question. So there's something that I didn't show in the single edge case. So in the single edge case, there is a link to a subgraph that really is an inhomogeneous random graph in the sense of Bollobach, Janssen, and Weerden. And we know there that the diameter is logarithmic. So I would believe that in this second setting, the square root of n tiny giant setting, the diameter is log n. That would be my guess, but we don't have a proof. In the first case, I would guess that the diameter is bounded. Tight. Well, at least typical distances would be tight. Diameter could be arising through rare fluctuations, so it may be a bit bigger than that. That would be my guess.
Okay, thank you, Remco.